right, so welcome everyone. So today we're going to finish up some loose parts of the graphics pipeline that we were discussing, that we were talking about the last couple of lectures. So you remember we started with the perspective projection, but then we made some assumptions that about the view frustum. We made the assumption that all our objects are within the view frustum, and also that we do not look into colors but only into grid models, and also that they don't overlap. And last lecture on Tuesday we already talked about the first two cases, the cases that the objects are not completely inside a view frustum. We talked about culling and clipping. In that relation I have to add something. Someone in the tutorial made me aware of that I said something in a way that might have been wrongly understood. I said that we talked about these two algorithms for clipping arbitrary polygons, and I said that we are only discussing them in 2D, but we can easily extend them to 3D. But that is only true for the first one, for the Sutherland-Hodgman algorithm, but not for the Weiler-Atherton algorithm, which is usually only applicable in 2D and does not generalize directly to 3D. But for the Sutherland-Hodgman algorithm, it is possible, because that was the one where we have, for example, a clipping region like this, and then we have a polygon like this. And then we can do the clipping by just extending one side of the view frustum, for example in 2D, from a segment to a line. In 3D we would do it then, of course, to a plane here in all directions, and then we just cut it off. And we learned a way to do this very easily, because if that line or that plane is represented in the implicit equation form, then we can just check if the objects, if a point here is equal 0, it is on the plane. If it is smaller than 0, it is below the plane, so inside of this area we want to keep, or if it is larger than 0, it is outside of it. Good. Okay. Yeah, so the only thing we didn't, and then we also talked about hidden surface removal, but for example in relation to backface culling, but also with the set buffer. And the only thing we didn't really completely talk about is about shading and texturing, so how to put color on those objects and not just have grid models, which is only partly true because a lot of this we have already discussed. We had a whole lecture about texture mapping, and also at the beginning we did a lot of talking about shading, and also you did a lot of this in the practical assignment. But I just want to repeat the shading part today and finish up some stuff that I haven't said. And also we didn't really talk about concretely how to put the color on these objects, on these triangles, to how to do it in an efficient way. And this is the first part. So we want to start first by not applying lighting, but just simply putting color on those objects, because so far we have only talked about really the points here. So we have them now from our abstract 3D representation put on to a 2D representation on the screen, but it's still an abstract object. So we just have, for example, in this case, the 3 vertices that represent this triangle. But when we want to draw it on the screen, of course, we have to also put color on the pixels that are inside of this triangle. So we have to really decide for each pixel, is it part of the triangle, and should we put some color on it or not? And of course, we could do that by testing for each pixel with this simple approach that we have for testing to which part, on which side of a plane or a line in 2D a point is, by just, and we could just test it for each pixel if it is inside or outside of the triangle, but that would of course be very inefficient. So it is much more efficient, of course, since we already know where the triangle is placed on the screen, if we just look around the area where the triangle is, because those are only the pixels that will be then get color or not, but the ones around them that are further away, of course, they will not get color. And one of the easiest ways to do this is, of course, to look at the bounding box of the triangle, because we know the bounding box is defined as the smallest axis parallel box that contains all the points from an object. So if it contains all the points of an object, and we also then of course if we just check those points, then we can be sure that the ones from the triangle will be the ones that we are actually drawing, and we do not have to check the ones on the outside. And finding those bounding boxes is very easy, because they're just defined by if we have a box, they are just defined by two vertices of the box. These two, we could of course also take these two, but if we do the ones that are marked with a circle here, then the equation to get this is very simple, because these are just the minimum x and the minimum y value is the left corner. So obviously this is x min and x y min, x and y over all the x and y values of the vertices of the triangle. And likewise, of course, this is obviously y max and x max. And this, of course, then gives us these two vertices of these two corners of our bounding box. So you see, it's a very simple way to do it. And then we save a lot of time in checking all those pixels that are not in the bounding box, because they will certainly not be in the triangle anyhow, so we don't have to color them, and we don't have to test if we want to color them. But still, with this bounding box, depending on the shape of the triangle, this can be very inefficient, because we have to test it, for example, in the second case here, a lot of pixels that are obviously not in the triangle. And even if we have like a polygon, it gets even worse. Then we can have even worse cases where we have to check a lot of pixels that are obviously not in a triangle. So we want to look into a more efficient way to rasterize not only triangles but general polygons. And to do this, we just make first some simplification. You remember, if we when we did the window transformation, we said that we have the pixels are usually the center of the cell, which is why for the windowing transformation we added this 0.5, or we subtracted it, I don't remember. But you remember we had this to shift this a little bit to come to the center of the cell. And this is also what we're doing here. We're just moving this here, so we can just do the calculations easier, or I can do the explanation easier. I don't have to always add this 0.5 and just look at the center. So we get like a coordinate system here that really has these individual pixels there. Usually I try to avoid to become too close to the implementation issues, but rather like to stay at the conceptual level here in the lecture. But of course, sometimes I cannot avoid this, especially when we're talking about really how to draw the pixels on the screen. So, but if we do this, then we have this nice coordinate system, and we can do the calculation nicer. And the idea of this, the algorithm that we use, it's a so-called scanline conversion algorithm. In general, you hear often scanline algorithms, especially in relation to geometric algorithms. The basic idea or the characteristic of a scanline algorithm is that you have a scene and you have a line that you move over that scene or over that window, and then at each position where you have the line, you do some operations with the objects that are at this position that is crossed by the line. So for example, in our case here, we move the scanline from the bottom upwards, and then we do operations, for example, at this position 3, and then we move it to the next position, and then we do the operations at this level, and then we move it to the next position and do the operations on this level. We could also, there are also scanline algorithms where they do where they move the scanline like this. You could also have a scanline algorithm where you move it like that. But in general, the point is that you have a line that moves over an area, for example, a window, and you do the operations at the position where the scan line is. And the second term, and obviously for the rasterization, we see here that the operations that we do here is basically we check what is the left intersection, what is the right intersection, and then we know, okay, this is the left intersection, this is the right intersection, so all the points in between must be points inside of the triangle, so we have to put color on those. So we see here that we can do all the operations with the scanline, and the scanline algorithms are often used in situations where you can do sorry, I lost the scanline is usually used in situations where you can do all the operations in one step, and the operation only depend on the actual position of the scanline or what you have seen before. And this is the second term here, the scanline coherence. Coherence means, in that context, when you hear coherence in an algorithm or in a technique, it usually means that it takes advantage of some regularities that you have in the data, and in this case it means that you can do all the operations based on what you have seen so far. So here, when you do the operations on the scan line, you do that based on everything you have seen so far, but what you're doing here, the operation, does not depend on what you haven't seen yet. And that is the big advantage of scanline algorithms, that they only work on what you have done so far, which means you are done by one scan, which means you have a linear runtime, which is of course always an advantage and very efficient. And here you also see, of course, that you do not even need to look backwards. You just need to look at this position and just need to find the left and the right intersection point to do all your operations on the scan line. But we will see now that looking backwards to the previous scan line will actually help us to calculate these intersection points quite easily. Good. So yeah, so let's first look at a specific situation. So one particular case, so for example, the scan line at the position 3. What we say here that when we have a scan line that intersects with a polygon, we have so-called active edges, which are the edges that intersect with the scan line at this particular position. So here, these are just these two here, the left and the right one. If we would look at this position of the scan line, then of course we would have 4 active edges. Now, like I said, if we know the intersections here of the scan line with the polygon, and if we know which is the left and which is the right one, then we know exactly which pixels we have to draw, which are exactly the pixels in the center of it. So we can of course calculate this intersection here by using these 2 points that we have, and then create the line equation. And then we have 2 lines here. We just calculate the intersection point of this line with this line, the intersection point of the scan line with this line, and then we have our 2 intersection points. And here I wrote down the slope-intercept equation for a line. We could also use different kind of representations. We haven't used the slope-intercept form very often. Here we're using it because it comes in quite handy, as you will see soon. So for example, here the slope-intercept form, just to repeat it, is defined by d, which is the distance, the intersection of the line with the y-axis. So in this case, I have drawn it very badly. If you would have drawn it correctly, you would see that this intersects at minus 0.5, which is why this is the correct value in the line equation. And the slope is defined as the value that you have to go up divided to the value that you have to go to the right to come to a position on the line. So you can take any difference of delta x and delta y. So these are the differences here. We usually call them, if we make a difference like this, delta y and delta x. But of course you see here, if you would have taken these two here, because the relative size stays the same, this is all the same, this all leads to the same slope, which in this case is, if we go one step to the right, we see we have to go 3.5 to the top, if you draw it nicer than I did here, and then you see this is a slope of 3.5. So we could use this to calculate the intersection points, but if we now comes the part where we take advantage of this coherence, that we already know the values from the previous intersection point, from the previous scan line, and we can use that to very easily calculate the intersection points of the new one by just adding a value instead of doing this division that we would need for the intersection calculation. And that is easily done if you look at this slope that we calculated. So I said here, here in this case I used 7 and 2. If you go 2 to the right and 7 up, then you are again on the line. So that means the slope is 7 divided by 2. And now if you think about how much do you have, how much does the x value change if you move from one scan line to the next? Obviously that is the delta x, delta y that changes here is just 1. So if you set here this to 1 and then bring the delta x on one side, obviously you see that it just reverses the slope here. So you have a delta x of 2 divided by 7, which means if you have a triangle here where you go up one step, delta y is 1, then this distance here must be 2 divided by 7, which is the delta x that we calculated here. So when we have this value here and we move up here, we know that the y value just changes by plus 1, and the x value of that point on the line changes by plus delta x, which is plus 2.7. So that gives us an easy way, starting from this point, to calculate all the intersection points step by step when we move the scan line upwards, because here we have the delta y, it's just plus 1 every time, and here we just add the plus delta x, which is 2 divided by 7. And we already know the starting point because that's the lower vertex of our segment here. And we also know the upper point. So as soon as our scan line has reached the upper point, which we can check because that's just the y value, if the scan line value is the y value of this upper point, then we know we're at the end of this segment, and then we also know that this segment is over and this is the last point. So these are all the intersection points that we need here to calculate, and we don't need to calculate an intersection point, we just start with one and then just need to calculate this delta x, and then we can add this delta x here. Good, so let's just quickly look into how we can phrase this into an algorithm. The algorithm is pretty simple. It's more about how to write down the data structure in a way that is efficient and obvious. And that is done by storing two tables that we use for this algorithm. One is the so-called edge table, which is just a list of the edges where the scan line starts. So for each edge that we have here, we have at the position, this is important, where the scan line starts, we have an entry for each edge. So we see here at scan line 1, there are two edges that start. So we have at scan line 1, 2 entries. At scan line 2, there is one edge that starts. So we have at 2 also have at 2 one entry. 1 we have 2 entries. And at 3 we have nothing. At 4 we have 2 edges that start. So we also have 2 entries here. And then we're done because no new edges start. So this is our edge table with three lines and 5 entries, and these entries contain the x coordinate of the lowest vertex. So for example, for this here we have 1 in both cases because they both start at the x value of 1. Here we have 9 because it starts at 9, and here we have 4 for both because they both start at x value 4. Now the next entry is the y coordinate of the highest vertex, which in this case is of course 8. So for these two edges, where do we have them? Here and here. We have 8. Oh wait, that was wrong. Here and here we have 8. This one is the x value, y value 2. And this one has 6, and so on, so you see it. And then we store this delta x value, which we see for the first one we already calculated it, that's 2/7. Here we see the x value is, if we go 1 to the right, if we go 8 to the right, we go 1 up, so the delta x is 8. Here it is -1/2, and so on. So this is the information that we store for each edge. Now, it's important to think about why we're storing this information. The point is that this is exactly all the information that we need to get this line segment. This is a unique specification of the line segment. Originally we specified it by just writing down these two vertices, but by writing it down in this way, we the only thing that we have not encoded here is the x value of this upper point here, but we have it indirectly encoded because we know the delta x and we know how often we have to add it, but because we stored the y value of this upper point here, and that's why we have all the information here that we need to describe this line segment. I'm pointing on this because it's important, because it's a common mistake in the exam that people, when they are supposed to write it down, forget to write down the index of the scan line. But that is important because it is the index of the scan line indicates the start of it. So if you don't have that index, you don't know where it starts, so you cannot really specify or reproduce these vertices correctly, or this line segment correctly. So this is also like a little trick question to figure out if people just learned to mechanically do the algorithm or if they really understood how it works. Good. So this is just how we store our polygon in a very way that is efficient now if we do the processing. And the processing is done by another data structure which is called the active edge table, which is initialized with exactly the values that we have in the edge table. But then for each step we move this scan line upwards, we change these values by adding this delta x value to the x value that we have here. So if we look at an example here, for example, we have the first entry, which is 1, 1, 8 to 7th, and 1 to 8. Now for the second scan line, if we move from that position to this one, we add, like we said here, we add the delta to the x, delta x to the x. We have here then 1 to 7th, 8 to 7th, and here we have 9 to 8. And then of course we have this new entry from here, which is 9, 6, minus 1/2. And now we see that here we see we see that the scanline index is the same as this upper y value, which means we reached the end of that segment already in one step, which means we are throwing it out. So in the next step we are not considering this one anymore. Actually, I crossed it out a little too soon because we are needing it here, of course, because we are here. We know now that this is our intersection point, and this is the right intersection point, so we have to color these here. And we know that this is the left intersection point and this is the right intersection point because we have the x value in here. So what we have to do when we do the processing here, when we add new points here, we have to be careful that we resort these lists based on the x value, because then we always know where the left and where the right one is, so we can do the coloring appropriately. It's another common mistake that people just write down the list with the segments, but they forget to sort them by the x value, which again is kind of an indication that they learned to mechanically do the algorithm but didn't really think about what it means and how try to understand it. Good. Yeah, I already said that if we have this situation here that the y value is the same as the scanline index, which that means that the scanline reached the end of this segment and then we remove it in the next step. So this is basically just the summary of this algorithm based on these two data structures. We start by initializing it with the initial data structure, and for each step we add the delta x value until we reach this highest y value, which is the end of the segment. And in between, if we sort them by x value, so this is a step that is often forgotten, if we sort them by the x value, then we know where the left and where the right points are, and then we can color them, all the pixels in between. Good. Yeah. And this is just I just wrote it down because I think it's so simple that it's too boring to do everything here and write it down. But I think it's also good for you as an exercise to really do it, and then here you have the solution to compare it. Good. Wait, I'm confused about the clock. Good. Yeah. So yeah. Yeah, that is in the implementation you would start with the 1. The reason why it's in the image, that is related to this, that we shifted them. So we are in the center of the 1, 1 is the center of a cell, and then we shifted it, and that's why in this diagram there is a 0, 0. But of course, if you, I was also confused about this when I saw this first. If you talk about the bounding box, you would not assume you would say there is an additional cell around there, which doesn't make sense. It is only because we shifted them. That's why we have it. Good. All right. So yeah. So this is a very efficient way to put color on our triangles, but it is also a very efficient way to do a couple of other things. For example, to fill the set buffer. We talked about the set buffer last time, how we can use the set values and store them in the set buffer to do hidden surface removal very efficiently, but we only talked about the set values here because so far we were only dealing with grid models, and I said kind of, yeah, in between you can just do a linear interpolation, which is of course true, but the question is how you can do it efficiently, and the answer is of course now with the scanline algorithm. So we can also use the scanline algorithm to do the set buffering. So we can do this with calculating this delta set value, which is pretty much the same as in the previous case. So if you think about it, so far we had here x0, y0, because we projected them to 2D, so we just have two values, x and y. And then we said, okay, this here is delta x, delta y is 1, and then we add just plus 1, and then we calculated for each step the delta. We calculated the delta x once, and then we also added the delta x to come to each point here, the next point on our line. And this delta x, delta y we got by taking just the slope of this here. So we took the slope, which is y1 minus y0 divided by x1 minus x0. That is our slope. I think we used the letter m somewhere there. And then we said, of course, if we set now this delta y to 1, then we have delta y divided by delta x equals m. Now, if this delta y is 1, then this is, of course, the delta x is 1 divided by m. Now, what we do here with the set value, because of course the set value, that's the thing that I said last time, we just carry it along because we need it later for, it's not part of the point anymore because we did the projection, but we carry it along because we need it for the hidden surface removal. And then we basically just interpret the set value in the same way. We do a linear interpolation, not between x, y here, but between y and z. So the set value is then just defined as we just get here in a similar way. We get an m set by just using the set instead of the x here, and in a similar way here we get also x set. So that is a little confusing. That shouldn't mean it follows from that, but it just means we can calculate it in a similar way. I'm just too lazy to write it down. Good. Yeah, in relation to the set buffer, there was also a question in the tutorial that first I was a little confused, but then of course I remembered. Someone asked about it, about transparency, and that is of course something that is a disadvantage of the set buffer because it is not supported, at least not with additional code, because of course if you have transparency then you need to store different color values, and most importantly the drawing order does matter because the set buffer just overdraws a value. If you get a new triangle that is in front of everything you have drawn, then you just draw it in front of it. But if some of them are transparent, or the new one that you draw is transparent, then of course what happened before is also something that is important. So the drawing order for transparency does matter, and not only which one is the closest, which is why it's per default not supported by the set buffer. There are tricks to do it, but per default it is not supported. And that kind of motivates lists also some other disadvantage of the set buffer. Another disadvantage is of course that depending on the drawing order, it could happen that you really overdraw an individual pixel several times. So you do a lot of unnecessarily computation of color values, which might be computationally expensive, or yeah, you have to trade off between, is it more expensive to find the order, the correct drawing order first and then only draw the first one, or risk of calculating a lot of triangles that you actually then are overdrawing, so you basically calculate them but you don't need them. And another problem is of course large memory requirements, which is not a problem if you have a hardware support by default, but if you implement it in software, then you need a lot of memory requirements. Good. All right. Yeah. Keep looking at this stupid watch here. Are there any questions about set buffering? No, because then we would move to the shading, which is another block, which is why I think it makes more sense to make a break now, and then continue in at 4 o'clock. All right, let's make a break.